ko, Advice Horizon Chaser. At narito po tayo ngayon sa Prince Hotel na kung saan ay tukayan natin itong nakakapanabik na paper presentation finalist na ito po ay programa ng National Academy of Science and Technology Philippines. Taon-taon ay sinusubaybayan po natin ang paper presentation of finalist na ito po ay mga kabataang scientist natin dito sa ating bansa. Ay nagsimula pa ito noong 1991 na kung saan ay binibigyan ng award itong ating mga kabataan na mga kung ano ang kanilang mga innovation or na itutulong o naiambag dito sa ating bansa. Ang itong nakakapanabik, so sino po kaya ang makakatanggap ng first prize winner ng 500,000 pesos mula sa Department of Science and Technology na ma-approve po itong proposal? So abangan natin yan. May napili po na 6 na finalists ang NAST para sa 2024 Talent Search for Young Scientists. Una, si Mr. John Andrew ALBAY ng University of Santo Tomas.
The energy input is here from my presentation is from the hot copy that I have. So the work, so basically this rotation of the wheel in my Stirling engine in this case. So, but with the limits of the thermodynamics and physics, is not all of this input energy will be converted into work. So some will be discarded into our environment. So in this case, the air surrounding our engine. So all of this engine, so they are basically defined by their efficiency or being described by their efficiency, how much work they can produce from the input energy. So this simple idea of having a temperature difference, a hot and a cold one, that can produce work has totally propelled the growth of the Industrial Revolution during the 1800s. So right now, this engine, so we already have a lot of innovations, ideal efficiencies. So an example is in our car. So we have our engines in our car. The input will be from our gas. So I think it's already, the price of gas is already high. So with the input of energy from our gas is, cars basically can only produce 25% of work. So we lose 75% of the energy. And the problem is, there are a lot of dissipative processes in engines. We have your friction, we need to cool our engines, so these energies will be all discarded to the environment. So we lose this energy. So as anyone who studies this engine, our number one question is actually on how do we improve these engines? So the obvious answer is we want to reduce the dissipative process. The harder question is how. And in our lab, so we have a different take on how to improve our engine. Is the idea is miniaturize our engine. It's actually engines that found in our cells, in our bodies. So an examples are these molecular motors. So they use chemical energy, they can do their work, this walking motion. So they can do their transport of cargoes inside our cells, or even the F180 pace, this rotation. And surprisingly, all of these machines, they are very efficient. We have a 60% and even 100% efficiency for the F1 motor. So, but the problem when we go small is the thermal noise. So, what does the thermal noise do? It's actually noise. For example, we have our particle will move randomly in this water. So the higher the temperature, the larger the thermal noise, then our particle will fluctuate more in our water. So this is the problem with it is right now our nanobio machines, we find that they are very efficient. They are very efficient, but the problem is in a noisy system. So it's that small. So with this size, we can already have an engine 100 times smaller than the thickness of our hair. So here, Then we have already our piston. So we applied our will produce the harmonic potential, the piston in our engine, and also the noise. So it can also control the temperature in our engine. So with only a single laser. So what we found for the engine is it works very similar to a macro scale. So our smaller engine works very similar to a larger engine. So we can observe the cycle of the thermodynamic processes from earlier is increasing, and also the trade-off of power and efficiency. So this is our old power engine. So how can we still replace their engine? Not in water, but in bacteria. And surprisingly, they found that this engine can outperform their classic engine. So this opens up a lot of new ideas on how to design engines, and it opens up questions on how can this, for example, this bacteria bath, how can they produce a efficient engine? So, but the problem in this, bacteria are very hard to control. So when you do experiments with bacteria, it's very hard to control them. Maybe 1 week they will produce different activity, the next day maybe I don't know what's, maybe the lazy bacteria will be the one, so they don't have a but in average this bacteria will show their proper activities. So here what we do is we did not use the bacteria. So again, we used our set up the optical feedback trap. So because we can easily control the piston, the harmonic potential, and the noise in our system. So in here, we replace our bacteria with the noise. Since we, as a physicist, we understand the effect of the bacteria, that this is just the noise with persistence. So the correlation of the effect of the bacteria is actually an exponential. So we can focus on two terms here, the capital T, OU. So you can imagine this as the strength of your bacteria as it hits your colloidal particle. So how strong your bacteria is. And the tau is the persistent time. So how long it will change in direction. So we focus on these two things, and the effect of this noise is actually on the fluctuation of our particle. So how will our particle move inside the piston? And surprisingly, this fluctuation translates to the effective temperature by the additional noise. So how much it will affect the movement of our particle. So here, understanding the noise. So again, we applied similar cycles with earlier. So we just applied our engine, and for comparison. So here, this one is our so it will change even only if we change our piston, if we tighten or untighten. And we found the efficiency is actually lower. So it's different from what we expected, that the effect of the noise actually lowers the efficiency. Then can we still improve our engine? So we tried to modify our control on the noise. So we just add another control on our noise, and then the effective temperature is always increasing in our engine. Check on the energy. So if it's less than A, we found that with the active noise, the engine has less work. But if it's greater than our factor, we can have the decay here, or the slope of the energetics is lower compared to the passive bath heat engine. And it translates to the efficiency. So we found that the efficiency at less than the critical factor, with the active noise, it is always less efficient. But at greater than the critical factor, we can always achieve a much better heat engine with the active noise. So here we further check if it's true at different temperatures. So we check at different temperatures. So at higher temperature, the behavior of the engine is it will reach a saturated efficiency. So even if how much we increase the temperature of our engine, so it will reach the saturated efficiency. But when we place the active noise in our heat engine, it can surpass some at certain levels of temperature difference. So indeed, on how we can achieve a efficient active bath heat engine, so with the presence of active noise, what we need to do is actually control our active noise. So for my talk. So I hope you have learned these 3 topics. So the basic idea of a heat engine. So right now, so even in a colloidal system, and we can also use a different reservoirs in our heat engine. An example is the bacteria bath. And if we, based on our learnings and our work, is if you use a bacteria bath, so it needs to be a photokinetic. We change the intensity of our laser, then the bacteria should also respond to these changes, that it will also increase the activity of the bacteria, thus producing a efficient engine. So what's next for my work is actually, all of my work is in the high efficiency, in low power. So we want to increase our engines in the high power, in the maximum power area, so that when we have this maximum power, then we can use this useful work of our heat engines that we can think of in the applications is in the microfluidic devices. And for our collaborators is they are doing the engines in electrical circuits, so they can also create a mini generators with the use of the microscopic heat engine. So again, I thank my funding agencies, the NAST, NTS from Korea. So again, thank you for listening for my talk. And good morning.
Thank you very much, Dr. Albay, for sharing us your very interesting topic, your research. So I know